Welcome to today's class on real analysis. Today we discuss some basic theorems on point set topology. The first theorem is if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. The proof is by contradiction method. Suppose that a neighborhood N of P contains only a finite number of points of E. So let Q1, Q2, etc. Qn belongs to N intersection E, which are distinct from P. So how this is the situation. So suppose that this is the neighborhood of P. Suppose that this neighborhood contains the points. Suppose this is the point Q1 and this is the point Q2 and this is the point Q3, etc. And suppose this is the point Qm for some m less than n, and suppose that this is the point some Qp, and suppose this is Qn, etc. So there is only finite number of points inside the neighborhood of P. Then you consider the minimum of the distances from P to Qns. So from this you can see that Qp is a point at a minimal distance from P. So suppose that this distance is r. This distance is r. Then you consider the neighborhood of P with the radius r. So you consider this neighborhood. This is here NRP. Then you can see that NRP contains no points of E. So which will contradict the fact that P is a limit point of E. So that's our proof. So let Q1, Q2, etc. Qn belongs to N intersection E, which are distinct from P. Put R equal to minimum of distance from P to Qm. For 1 less than or equal to m less than or equal to n. So you consider all Qms, find the minimum distance. This is R. This is the minimum of finite set of positive numbers, which is clearly positive, so that R is greater than 0. So you are taking the minimum of positive quantities, so that is positive. Then the neighborhood NR of P. So that is this neighborhood in the case of R2. Neighborhood NR of P contains no point Q of E. Other than P, such that Q not equal to P. So that P is not a limit point of E. So which is a contradiction to the fact that P is a limit point of E. Therefore, every neighborhood of P must contain infinitely many points of E. We prove a corollary to the theorem. A finite point set has no limit points. So proof is very simple. Since the set is finite, every neighborhood of a point in the set has only finite number of points. Therefore, it cannot be a limit point by the previous theorem. So proof. Let E be a finite set. Since E is finite, for P in E, NR of P, neighborhood of P, contains only finite number of elements. Therefore, P is not a limit point by previous theorem. Therefore, since P is chosen arbitrarily, therefore no point of E is a limit point. So this proves the corollary. Therefore, a finite point set has no limit points. Now we do some problems on closed set, open set, perfect set and bounded set. So this is a question. Discuss whether the following subset of R2 is closed, open, perfect and bounded. First question. A. The set of all complex numbers is set such that modulus of set is less than 1. So answer, we have modulus of set equal to 1 is the boundary of the set, modulus of set less than 1, and modulus of set less than 1 does not contain its boundary. Therefore, the set of all complex numbers set such that modulus of set less than 1 is not closed and it is open. The set is not perfect since it is not closed. It is bounded because the set is bounded since we can enclose modulus of set less than 1 in a disk of radius m greater than or equal to 1. That is, if the given set D is set of all set in C such that modulus of set less than 1 interior of the unit disk, and E is set of all set in C such that modulus of set less than or equal to m, where m is greater than or equal to 1, then D is contained in E. Therefore, D is bounded. So the set modulus of set less than 1 is open, not closed. Being it is not closed, it is not perfect and it is bounded. Consider the set B, set of all complex numbers, modulus of set less than or equal to 1. So let a D to be set of all set in C such that modulus of set less than or equal to 1. Then D is closed since D contains its boundary. You know that boundary of D is set of all set in C such that modulus of set equal to 1, the unit circle, so that is contained in D. Therefore, it is closed and therefore D is not open. Now, D is perfect since D is closed and all points of D are limit points. That is, you can consider every neighborhood of every point of D, then that will contain infinitely many points of D. This is because since every neighborhood of every point of D contains infinitely many points of D. So it is perfect. And consider E equal to set of all Z in C such that modulus of set less than or equal to m, where m is greater than or equal to 1. Then D, our set under consideration, is contained in E. Therefore, D is bounded. Now you consider another example. Example C, a non-empty finite set. So answer, let E be a non-empty finite set. Then E has no limit points. So by our theorem, E has no limit points. Now you know that the condition for closeness is that E contains all its limit points. So since E has no limit points, that condition is not violated. Therefore, the condition for closedness, the condition is that E contains all its limit points is not violated. Therefore, the set is closed. And it is not open. E is not open and E is not perfect since E is closed but no point of E is a limit point. Therefore, E is not perfect. Now, E is bounded for if Q1, Q2, etc. Qm are elements of E and let Tm be greater than the maximum of the distance between Qi and Qj. For 1 less than or equal to I, j less than or equal to m, where I not equal to j. Then n m of Qi for I is equal to 1 to etc. m contains E. Therefore, E is bounded. That's all for today.